In this example, we have 3 blades, so we got so-called double shear example here. We have 3 blades of steel, which of 2 of these blades are mounted into a wall, and then the 3rd blade is sandwiched between those 2 blades. So on the middle blade, we have force of 15 kilonewtons affecting to the left, and there are 6 rivets which are holding together this structure. Each of the rivets are of diameter of 8 millimeters, and we are asked to determine the factor for safety of the joint when the allowable shear stress or the allowed stress values are as follows. So shear for rivets 160 megapascals, surface pressure for rivets 250, and surface pressure for the plates 300. So, as always, first thing which we do is that we start with free body diagram. So, free body diagram, FBD. So I will draw the free body diagram of the center plate in this example. Because we have 6 bolts, I want to now, in this case, do the free body diagram in kind of like 3D shape. So I draw it like this. It's easier to visualize what's the case in here. Like so. And now in here we have 6 bolts in here, or rivets, 3 here and 3 in here. And then we have here the force 15 kilonewtons to left. So now in this example, when we have the force in there, and then we have these rivets which go through the plate like so. Each of these surfaces here have shear force. So on top surface we have 6 shear forces like this, and at the same time we also have them at the bottom surface. So now when we do when this structure is in equilibrium state, which means that the sum of all forces in horizontal direction, equals to 0, just like in all the examples prior to this one, we can now do the calculation. So we have 6 forces pointing to the positive direction, 12 forces, so be careful with these ones. So we have 12 times V pointing to the positive direction, and then we have minus 15 kilonewtons pointing to the negative direction, and this equals to 0. And this is our equation number 1. In this example, everything is aligned, so we don't have to take into account any torques or any moments, or we don't have any vertical forces, so only horizontal ones. And from this one we can easily solve out from equation 1. We can solve that the V is 15 kilonewtons divided by 12, which is 1.25. kilonewtons, like so. We could have drawn the free body diagram also from the top plate or from the bottom plate. If we did this free body diagram from the, for example, from the top plate, the case would be we would have the plate like so. We would have the plate like so. We have rivets there, 6 rivets. And then we have here the force. But now, since we have 2 plates, it means that in the top plate, where it's mounted to the wall, there's only 15 divided by 2 kilonewtons in here. And then underneath this plate, since this was the top plate, underneath this plate we would have 6 times V pointing to left. So you understand that now we have 6 V's and half of the external force, which would result into exactly the same external or exactly the same shear force. Okay, so let's erase that one. So that was for you to get the idea. So you can do this free body diagram in actually in 3 different ways in this example. Okay, so now we have solved the V. Well, what is the next thing? We're going to use the basic formula for the shear stress. So formula for shear stress was tau is V, which was the shear force, divided by the cross-section area into which the V is affecting. In this example, it means that the V is 1.25 kilonewtons, which is 1,250 newtons, divided by the cross-section area, which is pi times radius squared, and the diameter of the rivet was 8 millimeters, so the radius will be 4 squared millimeters squared. And from here we get that the shear stress in the bolt will be 25 megapascals. Like so. Well, what about the factor of safety for the shearing of the rivet? Well, the factor of safety for shearing of the rivet, let's do it in here. So F S is, so the maximum allowed shear stress in the bolt was 160 megapascals, and the shear stress which we calculated for the rivet was 25 megapascals. Megapascals get subtracted away, and hence the value in this example will be 6.4. So we could increase the shear force in these bolts by the factor of 6.4. Alright, what was the next thing? Now we have calculated the shear for the rivets. Now we have to calculate the surface pressure for the rivets. So let's take the center section of the rivet. So let's take the section which is inside this middle plate. So we start this once again by doing a free body diagram of this section here. So we have a cylindrical section of a bolt in there, like so, and then we have shear force V on top, and also shear force V on the bottom. And of course, when we have those shear forces, we must have here also force, which will be the force for surface pressure, because this thing has to be in equilibrium state. Well, we can draw from here, we can calculate the sum of all forces once again. So sum of all forces in horizontal direction must be 0, and therefore we can easily solve from here that the FSP two times V is 0, so we FSP is 2 times the external shear force V, like so. And the value will be 2,500 newtons. Like that. Well, now we can take the formula for the surface pressure. So the formula for surface pressure was sigma. Surface pressure is the surface pressure force divided by the projected cross-section area, D times H. So in this example, in here, the length of the cylindrical thing here is 10 millimeters. Where do we get the 10 millimeters? Well, the 10 millimeters is the thickness of this blade. In here, you can see that the thickness of this blade is 10 millimeters. And therefore, the length of this cylindrical section is 10 millimeters. And now, the D is the diameter of this cross section, so it will be quite simply just 8 millimeters. So we can easily calculate from here 2,500 newtons divided by 8 times 10 and the result will be 31 megapascals. And now finally we can calculate the factor of safety for this one. For the surface pressure, Fs is maximum allowed value. Surface pressure for Rivet was 250, so we calculate 250 MPa divided by 31 MPa, and this will give us exactly 8. Now we have checked the surface pressure on the middle part of the rivet, but we also have to check it for the top. The reason why we have to check it for the top as well is that the firstly the shear force is different and the plate thickness is also different. So let's draw a free body diagram of the top half of the rivet. So we have there, so I draw it like in here. So this here is the rivet, and here on the bottom surface we have V, and therefore we must have also on the opposite direction we must have the FSP, and we can see from here that in this example the FSP has to be equal to V because we're in equilibrium state. So it has to be 1,250 newtons. And from here we can calculate that the surface pressure is 1,250 newtons divided by the projected cross-section area, and the diameter is the same, 8 millimeters, multiplied by, and now in this case the plate thickness is 7 millimeters, so it's multiplied by 7, and the value for surface pressure in this case will be 22 megapascals. And factor of safety will be 250 MPa divided by 22 MPa, which equals to 11.3. Okay, so that's how you calculate the surface pressure for the rivets. You could also now, if you wish, you could also calculate the surface pressure for the plates.